We use computers all day, every day. But have you ever really stopped to wonder how they work? I mean, how do we humans actually talk to these machines? How does an idea in your brain turn into something happening on your screen? There's this huge communication gap between us and them. And today, we're going to build the bridge to cross it.
So, let's kick things off with the most basic question of all. You've seen it a million times in the movies, right? The hacker, the screen filled with green zeros and ones scrolling by. But why? Why that? Why not A's and B's or, I don't know, circles and squares? Well, the answer is actually pretty simple, and it's got nothing to do with what we chose. Computers speak in zeros and ones because, well, they physically can't understand anything else. It's a fundamental limitation that's literally built into their hardware. Okay, so to really get this, they've got to zoom in, and I mean way, way in. We're about to take a little journey deep inside the brain of the computer to see how it actually sees the world.
So here's the breakdown. At the heart of your computer, you've got the microprocessor, its brain. Now, if you could shrink down and look inside that brain, you'd see it's made of billions, literally billions, of tiny little switches called transistors. And a transistor is a super simple device. It can only be in one of two states. It's either got a high voltage going through it or a low voltage. It's either on or it's off. That's it. So to talk to these billions of simple on-off switches, we needed a language with just two symbols. So we gave them names. We call on 1 and we call off 0.
And that's it. That's the big secret. Binary code isn't just some abstract, nerdy concept. It's a direct, physical thing. A 1 is literally a little pulse of electricity, and a 0 is the absence of that pulse. It is the only language the hardware can physically, truly understand. So here's the thing. We have this machine that only gets on and off. But we humans, we're terrible at thinking in long, complicated strings of ones and zeros. This created a huge problem, and solving it led to this really fascinating evolution in how we chat with our computers.
Let's just track this journey for a second. Back in the 40s, programmers had no choice. They had to write everything in pure ones and zeros. We call this machine language, and as you can guess, it was unbelievably painful. So in the 50s, they came up with assembly language. This was a step up. It used short little words like add to stand in for binary code. Better, but still pretty clunky. And then finally, we developed high-level languages, the kind of stuff most programmers use today. And they look a lot more like human language, using words and symbols that we all recognize.
I mean, just look at the difference here. It is absolutely night and day. On the left, you've got this mess of binary code needed just to add two simple numbers. And on the right, the way we do it today, 5 plus 3. It's a huge shift from a language built for the machine to a language built for us. Okay, but hold on. This creates a brand new problem, right? If we're writing in a language that's easy for us to understand, how does the machine, which remember still only gets zeros and ones, how does it get the message? We need someone in the middle. We need to hire a translator. It's really just like this classic translator problem. You've got two world leaders, they don't speak a common language, they can't talk to each other without that person in the middle who's fluent in both. Well, our human-friendly code and the machine's binary code are those two different languages. You absolutely need a go-between. And in the world of computing, that translator has a name. It's a special program called a compiler. Its entire job, its whole purpose in life, is to take the intuitive code that we write and painstakingly translate it line by line into those long strings of ones and zeros that the microprocessor can actually work with. It's the real unsung hero of almost every piece of software we use. Okay, so now we have our human thoughts, and they've been translated into binary instructions. But where do those instructions actually live? And how do they get to the processor to be executed? This is where the rest of the hardware team comes in, and they play some very, very different roles. I want you to think about your computer storage, like the old fable of the tortoise and the hare. Your hard disk, that's the tortoise. It's slow, but it's reliable, and it can store a massive amount of information forever, even when you turn the power off. Then you have RAM. RAM is the hare. It is unbelievably, blazingly fast, but it has a terrible memory. The second you cut the power, it forgets everything. Poof, gone. So when you double-click an icon to open a program, what you're really doing is kicking off this race. The program gets copied from its forever home on the slow hard disk, the tortoise, and gets moved into the super fast but temporary RAM, the hare. The processor is way too fast to wait around for the tortoise. It needs the hare to feed it instructions at lightning speed. And of course, the reverse is just as important. When you hit that save button, you are telling the hair, that fast but forgetful RAM, to pass a copy of your important work back to the tortoise, the slow but reliable hard disk, to keep it safe for the long term. This is exactly why if your computer shuts down before you save, your work just vanishes. The hair, it just forgot.
So let's put this entire puzzle together one last time. You, the human, write code in a language you can understand. The compiler translates that into binary for the machine. When you want to run the program, you're loading it from the slow hard disk to the fast RAM. Then the microprocessor grabs those instructions from RAM and gets to work. And finally, you save your stuff, copying it from RAM back to the hard disk for safekeeping. It's really an elegant dance between all these different parts. When you step back and really look at it, what we've built is just incredible. We didn't make the machine learn our language, and we definitely didn't force ourselves to learn its native tongue. Instead, we built all these clever layers of translation and hardware systems to create this seamless bridge between two totally alien ways of thinking. For decades, the whole game has been about making our conversation with machines feel more, well, human. But now, when you see technologies like Neuralink starting to emerge, we're getting close to a future where we might skip language altogether. And it leaves you with this one last big question. What happens to this amazing bridge we so carefully built when we can just plug our brains directly into the machine?